I was sitting in the back of a dimly lit briefing room at a defense expo last week, watching a veteran aerospace engineer scroll through his tablet. He had this smug, almost nostalgic smile as he talked about the F-35. To him, it wasn't just a jet. It was the computer that happens to fly, an untouchable ghost in the machine. He pulled up a graphic of the aircraft's sensor fusion, tapping the screen with a rhythm that suggested total certainty. "Nothing else even comes close," he whispered, calling it the God's eye view. He was convinced that as long as the U.S. held the lead in software, raw physical power simply didn't matter. He dismissively waved off news about China's J-20, calling it a heavy target with a loud radar. But then the conversation shifted to the hardware side, specifically the delays in the TR-3 backbone and the elusive NAPG-85 gallium nitride radar. I showed him a recent analysis of the J-20's massive nose cone and the sheer power output of their integrated GaN arrays. His smile didn't just fade, it curdled. Suddenly, the copycat wasn't a joke anymore. He started pacing, grumbling about supply chain betrayals and how rare earth export limits were a strategic stab in the back. The calm, clinical observer was replaced by someone visibly rattled, lashing out at the very industry he'd just been praising. That sudden pivot from absolute technical arrogance to a panic search for a scapegoat is exactly where the air superiority debate sits right now. We've moved past the era of undisputed exceptionalism into a gritty, high-stakes sensor race where the rules are being rewritten in real time. But is the J-20A truly the 5.5 generation juggernaut leaving the U.S. in despair, as some headlines claim? Or are we just looking at a new asymmetric reality where better depends entirely on who shoots first?
That's a powerful story because that exact moment, that pivot you saw in that engineer, that's the story of the last 5 years in aerospace. It's the moment the abstract confidence in software collides with, hard physical reality.
Exactly. It's the collapse of what you could call the software safety net. For 20, maybe 30 years, the prevailing belief in the West has been that any deficit, in aerodynamics or raw power could be patched over with smarter code.
Right. The doctrine was that we could process the battle space faster than the adversary could fly through it. The F-35 is the ultimate expression of that idea. It's not a fighter. It's a flying data fusion center.
The flying computer narrative. And it worked. It was an unbeatable strategy when the gap in processing power was absolute. But that engineers panic. It suggests the hardware gap is now swinging violently in the other direction.
We are seeing a forceful return to what you called tangible power. This isn't about elegant algorithms anymore.
No. It's about physics. It's about the brute force of the electromagnetic spectrum. It boils down to who can generate more watts of power, who can manage more heat, and who can manufacture purer crystals at an industrial scale.
We're moving the conversation from the abstract to the concrete. The sensor war, as it's being called, isn't really a debate about code anymore. It's an industrial competition.
A competition to see who can build the bigger, more powerful eye, who can see and lock and kill from further away because their materials are just flat out better.
So our mission here is to, strip away that comfortable Western narrative of software supremacy and look at the gritty physical reality of China's industrial advantage. We have to look at the J-20A not as just an airplane,
but as the tip of the spear.
The tip of a very, very large industrial spear. It's the delivery system for a national strategy built around a single material.
To really understand the scale of this, and the philosophy behind it, we have to start at ground zero. Not with the pilots, but with the people in the labs. We have this perspective from a senior materials engineer in Chengdu. Let's just call him Zhang.
Okay.
Zhang works in a high-intensity lab. His entire world, professionally speaking, revolves around one single metric: the crystalline purity of gallium nitride wafers.
So he's right at the source. This is the very foundation of the entire advantage we're talking about. The sensor war, for him, is not a forum debate. It's a physical object he holds in his hand.
Exactly. And he sees reports about the U.S. F-35's Technology Refresh 3, or TR-3, being stalled not by lack of money or engineering talent, but by millions of lines of code that just won't cooperate.
The software integration nightmare?
Right. And he views this with a kind of a cynical satisfaction. From his perspective, the West has become totally lost in the abstract. They're obsessing over debugging loops, trying to achieve this kind of abstract perfection in the code.
While his team and the entire ecosystem around him in Chengdu has been focused on one thing:
physical output, scaling up the manufacturing of high-power gallium nitride modules, just making more of them, better and faster.
So when he looks at the J-20A, he doesn't just see a sensor.
No, he sees a massive physical statement of industrial capacity. His whole philosophy is incredibly blunt, and it's this: You cannot fire a software update at an incoming missile. The tangible physical output of his lab is fundamentally superior to the abstract perfection of code that might be ready next year or the year after.
That's the core argument right there. Physical output trumps abstract promises, and that philosophy explains everything else. It explains why China has poured so much national will into mastering the material science of gallium nitride, or GaN.
Let's really get into the weeds on that then. Why GaN? Why is this one material the foundation for this entire shift in air power? The industry standard for decades has been gallium arsenide, GaAs. It's well understood, it's reliable.
It is, but it has a ceiling, a physical limit. The difference boils down to something in solid-state physics called the band gap. GaN is what we call a wide bandgap semiconductor.
And in practical terms, what does that mean for a radar?
Okay, so think of the band gap as a material's ability to withstand electrical pressure before it breaks down. A wider band gap means you can hit it with much, much higher voltages, and it can operate at much higher temperatures.
So it's just tougher.
Fundamentally tougher. For a radar's transmit-receive module, this translates into power density. GaN can handle power densities that are, and this is a conservative estimate, 5 to 10 times higher than gallium arsenide.
5 to 10 times. That's not an incremental improvement. That's a revolutionary leap.
It's a total game changer. You're pumping 5 to 10 times more energy through the same amount of physical space. When you build an ASA radar, an active electronically scanned array out of thousands of these modules, the operational impact is just profound.
Your detection range explodes, obviously.
It goes way out. Your resolution, your ability to distinguish between multiple small targets gets incredibly sharp. But the real killer application is its resistance to electronic warfare.
The ability to burn through jamming.
Imagine an adversary is trying to blind your radar by flooding it with noise. A gallium arsenide radar might get overwhelmed. But a GaN-based system has so much raw power, it can simply overpower that jamming signal. It's like trying to drown out a foghorn with a whistle. It gives you a level of spectral dominance that older materials just can't compete with.
But, as with everything in physics, there's no free lunch. Pushing that much power through a tiny chip must generate an insane amount of heat.
An immense amount. And that right there is the thermal bottleneck. Heat is the #1 enemy of high-power electronics. You can have the most powerful chip design in the world, but if you can't get the heat out fast enough, the internal temperature skyrockets, performance collapses, and the component it cooks itself to death.
So the traditional Western approach to this has been essentially better plumbing, more complex liquid cooling, bigger and heavier heat sinks and exchangers.
Right. Treating it as an external problem. Bolt on a better cooling system. But this adds weight, it adds complexity, and it adds more points of potential failure. The real breakthrough was in looking at the problem differently.
This is the research coming out of Zhejiang University from Zhuok's team. They didn't look at the plumbing outside the chip. They looked at the atomic structure inside the chip itself.
This is the elegant part of the solution. They correctly identified that the biggest thermal obstruction wasn't the external cooling system, but the bonding layer inside the chip package. Specifically, a layer of aluminum nitride that sits between the GaN chip and the heatsink.
And what was wrong with that layer?
In standard manufacturing, the crystals in that layer grow in a very irregular, chaotic way. Imagine the heat, which is carried by vibrations called phonons, trying to travel across a road full of potholes and cracks. It gets scattered, it gets trapped, it can't flow smoothly.
It's a thermal traffic jam at the microscopic level.
So what Zhu's team did was figure out how to restructure that road. They developed a new manufacturing method to grow those aluminum nitride crystals in a perfectly uniform, aligned structure.
So they smoothed out the potholes.
They turned a thermal bottleneck into a thermal highway. The heat can now flow out of the chip with almost no resistance. It's an incredibly sophisticated piece of material science.
And the performance numbers on this are staggering. They're reporting a 33% reduction in thermal resistance.
Huge. But what that translates to in performance is a 40% increase in the radar module's power output and efficiency.
Without increasing the chip size and without increasing its energy consumption. It's pure efficiency gained by better physics.
That 40% is everything. It means the J-20's radar can be driven harder for longer than a comparable Western system that's burdened by heavier, less efficient external cooling. It's a more elegant and ultimately more powerful solution.
But a breakthrough at a university lab is one thing. Turning it into thousands of high-reliability modules for a frontline fighter jet is a completely different challenge. This brings us back to the supply chain, the point our engineer Zhang was making.
You can have the best recipe in the world, but it's useless if you don't own the farm that grows the ingredients. This is where China's long-term strategy becomes so apparent.
It's about controlling the entire vertical, from the mine to the missile. And it starts with the raw materials. China produces something like 68% of the world's raw gallium.
And even more critically, over 90% of the refined weapons-grade gallium needed for this kind of semiconductor manufacturing. That's not just a majority, that's a monopoly. It's a stranglehold on the foundational element of modern warfare.
And they built this dominance through a very deliberate strategy: civil-military fusion. This is the hidden thread connecting everything. They didn't just decide to build a great radar for a fighter jet.
No, that would have been too slow and too expensive. Instead, they identified GaN as a key strategic technology for the 21st century and pushed it into the civilian sector first.
That G-base stations.
Billions of them. Power electronics for electric vehicles, high-speed rail control systems. They used the enormous scale of their domestic civilian market to drive the technology down the learning curve.
So the civilian market essentially subsidized the military's R&D. It paid to work out all the manufacturing kinks, to improve yields, to lower the cost per unit.
They built a massive, reliable, high-volume supply chain for the civilian world first. They perfected the process. Once the technology was mature and the industrial base was robust, the People's Liberation Army simply harvested the capability. It was ready and waiting.
Which puts the U.S. and its allies in a very difficult position. You could almost call it a silent sanction. When Beijing puts export restrictions on gallium and germanium, as they have.
It's not a symbolic gesture. It has immediate practical effects. It directly impacts the production lines of their strategic competitors.
The delays we're seeing in the F-35's new AN/APG-85 radar program, for example, those aren't just software problems. They are, at their root, industrial and supply chain problems. The U.S. simply lacks the domestic capacity to mine and process these materials at the scale required for a full fleet-wide upgrade.
It creates a dangerous dependency, and the result is a situation where the U.S. is arguably a generation behind in deploying these next-gen phased array radars, not just in jets, but across all platforms, tanks, ships, air defense systems.
Because the industrial depth is just not there.
Yeah.
Meanwhile, China has the raw material, they have the advanced processing capability, and they have the final assembly lines running at full tilt.
It's a complete end-to-end sovereign capability, and that material foundation allows for a completely different design philosophy when it comes to the aircraft itself.
Transition. This physical advantage translates into a different way of thinking about what a fighter jet should be.
Yeah.
And to understand that, we have the perspective of a veteran PLA-AF test pilot. Let's call him Old Wang. Old Wang is transitioning to the J-20A from older platforms, and he has a very specific view. He completely rejects the Western term flying computer. He calls the J-20A a fortress of physics.
Fortress of physics. That terminology is incredibly instructive. A fortress is about strength, resilience, physical presence. It's not about being clever or abstract.
Exactly. For him, the physical attributes of the airframe, its large size, its internal volume, its sheer power generation, these are the primary guarantors of survival. Not software, not complex networking that might fail.
He's betting on the laws of physics, not on lines of code.
He sees the J-20's large airframe not as a failure of miniaturization, which is the common Western critique, but as a deliberate and intelligent design choice. That size provides space.
Space for fuel, obviously, but more importantly, space for power and cooling, and space for a much, much larger radar antenna.
This is his core point. To Old Wang, prioritizing a massive radar aperture is a tangible guarantee of safety for himself and for the nation. It's a physical advantage you can count on. He views the Western reliance on sensor fusion, stitching together data from smaller, less powerful sensors to create a complete picture, as a form of systemic inefficiency.
He's saying it's a workaround, a complicated software solution to fix a fundamental hardware deficit.
That's his critique. He looks at the F-35's endless software delays and sees it as a form of civilization degradation, a sign of a state that is so complex, so bogged down in process, that it can no longer deliver on its fundamental promises.
Wow, that's a heavy critique. It's not just about jets anymore. It's a judgment on national capacity.
Superior reach, the ability to see and shoot first, is the direct result of a state that builds for the now, a state that values the bird in the hand, which is a powerful working piece of hardware over the two in the bush. The promise of perfectly fused data from a software update that's perpetually 6 months away.
This pilot's perspective really gets to the heart of the latecomer advantage. Chinese engineers had the benefit of watching the F-22 and F-35 programs unfold. They could analyze their strengths, but more importantly, their inherent limitations.
And the primary limitation of the F-35 in particular was its size. It had to be a multi-role fighter. It had to operate from aircraft carriers, so its airframe, and specifically its nose cone, had to be compact.
And that puts a hard physical cap on the size of the radar you can fit inside it. Physics is unforgiving on this point. The size of the aperture, the antenna, is the #1 variable that determines a radar's gain and resolution. A bigger dish here's better.
And the J-20's nose radome is visibly significantly larger than that of the F-35 or even the F-22.
Let's look at the transmit-receive modules, the little engines that make up the AESA radar. The F-35's APG-81 has about, 1,676 of them?
Yes, and the F-22's APG-77 has a bit more, around 1,900.
Right. Now, the estimates for the J-20's Type 1475 radar, the GaN-equipped version, put the module count somewhere between 2,000 and 2,200. Some analysts even suggest it could be higher.
So it's not just a slightly bigger array, it's a whole other class of sensor.
It's a massive array. And remember, each one of those 2,200 modules is a GaN module capable of handling 5 to 10 times the power density of the older GaAs modules in the F-22.
You combine the greater number of modules with the higher power of each individual module.
And the result is an explosion in total power output. The reports we're seeing suggest the J-20's radar achieves at least 50% more effective power than the F-22's, reaching peaks of around 24 kilowatts. That is an astonishing amount of energy to be directing from the nose of a fighter.
Now, the old critique used to be that Chinese packaging technology was behind, that they might have a big space, but they couldn't pack the modules in tightly enough to use it efficiently.
That was true maybe a decade ago. But that gap has been closed, and closed rapidly. The sheer scale of their 5G rollout forced them to become world leaders in high-density 3D packaging. And when you combine that with the superior thermal management solutions we just discussed, that thermal highway, you solve the overheating problem.
So they can pack the modules in tightly, and they can run them at full power without them melting.
And the operational result is unprecedented detection ranges. We're seeing claims, which seem credible given the physics, of tracking stealthy targets at distances well over 200 kilometers.
This completely changes the tactical equation. The F-35 is designed as a stealthy quarterback. It's supposed to use its low observability and sensor fusion to sneak in close, gather data, and share it with the network.
It's a networked asset, but right now that network is broken. The F-35 fleet is hamstrung by the TR-3 software crisis. Deliveries have been halted. Even the existing planes are struggling with overheating issues in their legacy hardware because the new software is too demanding.
And it has kinematic limitations too. It's slower with a Mach 1.6 speed limit and a lower operational ceiling around 15.5 kilometers.
Compare that to the J-20. It was designed from the ground up for air superiority, like the F-22, but with 21st century materials. It's faster, Mach 2.0 plus. It flies higher, over 20 kilometers.
Which gives it a huge kinematic advantage. A missile launched from higher and faster has more energy right from the start. It can fly further and faster, giving the target less time to react.
And this all feeds into their operational strategy. They're not trying to play the F-35's game of stealthy, networked warfare. They're using their physical advantages to create what some call a wall strategy.
Using that incredibly powerful long-range radar to establish a defensive envelope, a barrier, maybe 500 miles off the coastline.
A barrier of sensor coverage. They can see incoming forces stealthy or not long before those forces can get into their own effective sensor or weapon range. It's a strategy of denial based on raw physics.
If you can see the adversary first, and you can shoot first from well outside their range, their fancy sensor fusion and networking capabilities become irrelevant.
You've already won the engagement before their system can even come into play. It's a checkmate based on physics.
And this brings the whole picture together, connecting the aircraft in the sky right back to the industrial base on the ground. Which leads us to our third perspective, from a man named Lou. He's an infrastructure planner for ultra-high voltage power lines.
So we're going from material science to piloting, now to the electrical grid.
Exactly. Lou's job is to oversee the power grid that feeds China's main aerospace and high-tech manufacturing hubs. And for him, the connection is not abstract. It is direct and absolute. He sees a one-to-one correlation between the massive state investment in electrical infrastructure and the power of the J-20's radar.
He's identifying the ultimate root of the capability. You can't have high-power manufacturing without high-power, high-stability electricity. Building these advanced GaN radars requires clean rooms, precision manufacturing, and enormous stable loads of energy.
And Liu's perspective on the West is similar to the pilot, Old Wang's. He sees the Western reliance on abstract software solutions as a symptom of a society that can no longer manage big, ambitious, physical industrial projects.
A society that can't build.
That's his view. To him, the GaN radar is more than just a military component. It's the ultimate proof of a resilient civilization that is still grounded in physical reality. His core argument is that military hardware is the final report card for a nation's infrastructure. Tangible power, electricity, materials, factories is the only true measure of national health.
This is the civilization resilience argument. And when you look at the evidence, it's compelling. The U.S. struggles to get funding to upgrade its aging power grids. Its shipyards can't keep up with maintenance schedules. You see bottlenecks everywhere.
While China's state-led, results-oriented approach builds the capacity first. They build the dams, the power lines, the factories, knowing that this infrastructure will then enable the next generation of technology.
It creates a fascinating strategic paradox. The entire U.S. system bets on sensor fusion. The idea of networking many disparate, smaller, less powerful assets to create a whole that is greater than the sum of its parts.
China, on the other hand, is betting on robust physical infrastructure, building bigger, more powerful individual assets, supported by a stronger power supply and a completely self-sufficient supply chain.
And here's the risk in the American approach. If the software fails, as we're seeing with the TR-3 delays, the entire system grinds to a halt. The hardware is useless without the code to run it.
Whereas in the Chinese model, even if their software is only, say, 90% as good, their superior hardware physics might win the day anyway. Good enough. Software running on superior hardware is a powerful combination.
Then you have to consider the sheer industrial scale. In 2020, J-20 production was maybe 20 aircraft per year. Slow, almost boutique production.
Now, the latest projections for 2025 have that number at 120 per year.
That's a six-fold increase in 5 years. That's not just ramping up, that's an industrial machine hitting its stride.
And here's the really crucial detail. All 120 of those jets are for the PLA. There are no export customers. Compare that to the F-35, where the annual production, while high, is split among 19 different partner nations.
So the net increase in China's domestic fleet is enormous. They're projecting a fleet of 1,000 J-20's by 2030. That kind of pure national capacity, the ability to churn out that many high-end platforms for yourself, is a strategic deterrent in its own right. It's the classic saying, quantity has a quality all its own.
And finally, that quantity of high-quality platforms needs a tactical edge. We have to talk about the weapons, the long arm of the J-20.
The PL-15 missile, its range is estimated at anywhere from 150 to over 200 kilometers. It significantly outranges the U.S. AM-120 series missiles.
But the range is only half the story.
Yeah.
The really revolutionary part is the seeker head in the missile itself.
It's a miniaturized GaN-powered AS radar. They've managed to shrink that same core technology advantage down and put it in the nose of a missile.
So the whole kill chain is GaN-powered. The J-20's massive radar detects a target from hundreds of kilometers away. It launches the PL-15, and then the missile's own powerful jam-resistant GaN seeker takes over for the final kill.
The dev combination, and there are already reports of its successor, the PL-17, which is an ultra-long-range weapon designed to target high-value assets like tankers and AWACS planes.
And beyond just seeing and shooting, that massive ESC radar on the J-20 serves another purpose, doesn't it? It can be used as a communications node.
And that huge array of transmit-receive modules isn't just for radar pulses. It can be reconfigured on the fly to act as a high-bandwidth directional communications link.
So it can transmit maps, video, huge packets of targeting data to satellites or other aircraft.
And because it's powered by GaN, it has the raw power to push that signal through intense enemy jamming. So even though this philosophy is hardware first, that hardware enables networking functions that can rival the F-35, but with a more robust physical layer. It's the smarts inside the brute.
And this isn't the end of the road. We're already seeing the J-20A being upgraded with the new WS-15 engine, which will improve maneuverability, supercruise, and crucially power generation for these advanced sensors.
And the industrial machine is not stopping. They're already rolling out the J-35A, a medium stealth fighter for their carriers, and you hear constant discussion of their sixth-generation concepts. the J-20 isn't the final product, it's a statement of intent. The machine is just accelerating.
Which brings us back to that engineer in the briefing room. His sudden pivot from, total arrogance to panicked scapegoating. It starts to seem not like an overreaction, but maybe the only logical reaction when you're confronted with this data.
His confidence was built on a set of assumptions that are no longer valid. The entire Western approach bet on abstract perfection, perfect software, and on hyper-efficient globalized supply chains.
In China, bet on the opposite. They bet on physical resilience, on GaN dominance, and on sovereign state capacity and infrastructure. They chose concrete over the abstract.
And right now, in this sensor race, it looks like the side that controls the physics and the factory floor is pulling ahead.
We often talk about the fog of war, but perhaps the real danger we're facing now is the fog of sophistication, the belief that complexity and clever code can indefinitely outrun raw physical capability. When we look at the J-20A's massive arrays, the humming factories behind them, and the integrated supply chain that feeds them, you have to consider the new reality. In a conflict where a single software glitch can ground an entire fleet, we are witnessing the inevitable return of results-oriented power, where the winner isn't the one with the smartest code, but the one who can simply keep the lights on and the radar running.